learning from trial and error, just acquiring a new skill by, well, messing around in the world. That is really the signature move of biological intelligence. It's how we adapt, how we get that muscle memory.
Right. It's the difference between, say, memorizing a map and actually being able to drive a new route in heavy traffic.
Exactly.
One is static knowledge, the other is a dynamic procedure.
And that's where massive AI agents, the ones built on these huge language models, they often just hit a wall. Once they're deployed, they have these incredible foundational brains, but they really struggle to learn new step-by-step how-to knowledge in real time.
It's like a kind of procedural amnesia.
Yeah, exactly, which really limits how useful they can be in, these fast-changing digital worlds.
We spent so much time trying to give these agents good memories, and you can really break down what they need to learn into two main classes. The first class is facts.
Yeah.
These are atomic, context-independent bits of information.
Yeah.
User ID, shipping address, that kind of thing.
And we've gotten pretty good at that. You see frameworks like Memzir that are great at storing that kind of long-term factual memory.
Right, using RAG to pull up documents, snippets.
It works for general knowledge.
But that second-class procedures, that sounds like the real challenge.
That's the bottleneck. Yeah. Procedures are the established state-dependent ways of doing things.
So not just what something is, but how you do it.
Exactly. Think how to troubleshoot a failed login with a specific error code or, the right sequence of filters to find a report on your company's intranet.
And that knowledge, it's not static, is it? It depends entirely on what you're seeing on the screen right at that moment.
Precisely. If a website changes a button's color or a new pop-up shows up, the whole procedure can break. The agent has to learn it all over again on the fly.
So it's the difference between knowing the ingredients for a recipe
and having the actual skill to cook it when your oven is acting up and you're missing a pan. Right. And that is our mission for this deep dive. We're looking at a solution that is designed specifically to fill that procedural learning gap. It's called PROCS-IS. That's procedural recall for agents with experiences indexed by state.
It's a mouthful.
It is, but we're going to unpack it. We'll look at how this state-dependent memory works, why it borrows from human psychology, and then dig into the hard data from the researchers at Altrina.
And that data shows the impact it has on agent performance in, real-world scenarios.
Yeah, we're basically looking at how an agent can learn complex, adaptable skills after its main training is already done.
Our goal here is to see how Praxis helps agents go from being just passive knowledge bots to active learners of dynamic practical skills.
So let's start with what doesn't work. Why did the early attempts at this just fall apart?
Well, the first approach was something the researchers call a priori procedural specification.
Which is a very fancy way of saying.
There's a fancy way of saying a human writes a giant rule book, a standard operating procedure, and you just feed that to the agent.
Ah, the rule book approach.
Right. And you're treating the procedure like it's just one huge fact to be memorized.
That sounds fine for a simple, unchanging system, but for the real world, it's a non-starter.
It's a non-starter for, well, three big reasons. First, a lot of procedures are learned by watching, not by reading a manual. You learn a new piece of software by clicking around, you watch a YouTube video, you don't read the 300-page user guide.
Right, that undocumented sort of tribal knowledge.
Exactly. And second, there's the combinatorial problem.
The edge cases.
The sheer number of edge cases. You just can't write a rule for every possible error message or every variation of a pop-up. The rule book becomes enormous and incredibly brittle.
And then the third reason, which feels like a very modern problem, is just the speed of change.
Absolutely critical. Procedures go obsolete so quickly because the websites and apps they run on change constantly.
We're in an era where AI design tools are literally generating and updating web pages all the time.
Which means agents are always being pushed into new situations their training never saw. A static rulebook is useless if the login button moves every 3 weeks.
And that's why the web is such a perfect and maybe cruel testbed for this. Everything we do online, searching, filtering, logging in, it's all a multi-step procedure.
It's all sequence dependent. And that's where systems like RAG, which are great for facts, they just break down.
They can tell you what the return policy is, but they can't actually complete the multi-step return process on the website for you.
Exactly. They are built for text and conversation, not for these stateful visual interactive environments like a browser.
So we need a memory that's not for text recall, but for remembering successful sequences of actions, which I guess brings us right to Praxis.
Right. And Praxis is a A really elegant solution because it's inspired by a concept from human psychology.
Oh, interesting.
Yeah, something that's been around for decades.
Ah,
State-dependent memory.
I think I know this one. That's the idea that your recall is better if you're in the same state you were in when you learned something, right?
That's the one.
Like, if you study for a test while listening to jazz, you might actually do better on the test if you listen to that same music. The context is a trigger.
And the agent is borrowing that exact idea. Praxis is a lightweight mechanism that stores the consequences of successful actions.
Okay.
So when the agent needs to decide its next move, it looks for a memory by matching two things: the current environmental state, what the screen looks like, and its own internal state, what its goal is.
Ah, that dual matching is the key.
It's everything.
So a simple memory might just say, I clicked the blue button, but Praxis remembers I clicked the blue button because I was trying to log in and when the screen looked exactly like this.
Precisely. If the agent only remembers the action, it might just click any blue button it sees.
Which would be chaos.
But if the procedure is tied to the state, like a specific login failure screen, then it only retrieves that action when that specific context happens again.
So let's make this really concrete. What actually goes into one of these memory entries? The researchers break it down to 4 parts.
They do. The first 2 parts define the state before the action. First, you have the environmental snapshot.
The before picture?
Yep, what the agent saw, visually and textually, on the page right before it did something.
And second is the internal directive.
That's the agent's goal. Was it trying to log in, add something to a cart? It's the mission.
Okay, so you have the context. Then what?
Then you have the 2 central pieces. Third is just the action taken.
The click, the typing, the scroll.
The observable behavior.
Mm.
And fourth, and this is critical, is the consequence snapshot.
The after picture, what happened next?
Did the login work? Did the item get added? This part validates whether the action was a good one in that specific state.
And all this was tested using a specific agent, right?
Yes, the experiments used Altrina, which used to be known as Tessa. It's a frontier agent that operates in these computer environments and perceives things both visually and textually. It's a great stand-in for a digital assistant.
And pre-access eyes isn't like retraining Altrina's core model.
No, not at all. It's just augmenting its decision-making. It's integrated to modify the agent's action selection node.
So the part that decides what to do next.
That's the critical juncture. When Altrina needs to make a decision, it queries pre-accesses for these relevant state action result examples and uses those past successes to guide its choice. It's adding real-time experience to the process.
Which brings us to the data. How do you test something like this against the, chaos of the real internet?
Well, you need a really rigorous and maybe more importantly, a reproducible testing ground.
Okay.
So they used what's called the REAL benchmark. This isn't live web scraping. REAL uses deterministic clones of 11 common websites and 112 everyday tasks.
Deterministic clone, so perfect repeatable copies.
Exactly. It makes sure that when you test the agent, the website isn't just randomly changing on you.
That's a really important detail. It means any performance boost is actually from the learning, not just from luck.
It isolates the variable.
So what was the baseline? How were these top-tier agents doing before breaks?
It's not great. It really shows how hard these general web tasks are, even the frontier models with just, naive scaffolding.
Meaning without a good procedural memory?
Right. They only achieved about a 41% success rate on these tasks.
41%. Wow, that's a massive failure rate. If a human assistant failed nearly 60% of the time, they wouldn't have a job for long.
It really shows that raw intelligence isn't enough. You need experience, you need habits.
So that 59% failure rate is the room for improvement.
That's the gap that post-training procedural learning is designed to fill. And this is where you see the power of pre-access.
Because it's providing these saved examples, these exemplars, to the agent in real time. And the improvement shows up across 3 really critical dimensions:
accuracy, reliability, and efficiency.
Let's start with the big one. Accuracy. They tested this across a bunch of different models, right? Llama 4, GPT-5.
Yep, Gemini 2.5, Flash, a whole range. And across all of them, the average task completion accuracy went from 40.3% up to 44.1%.
Okay, a 3.8% jump might sound small to some people, but on complex, multi-step tasks, that's actually a pretty big deal.
It's a very robust lift, and it applies generally no matter which underlying model you use. In a commercial setting, think about what that means.
Fewer failed jobs, less need for a human to step in and fix things.
Tens of thousands fewer maintenance cycles if an agent is doing millions of tasks. Those memory traces provide these reusable priors that guide the agent. It's giving it a history of success to draw on.
Okay, so it gets things right more often. But what about reliability? For a business, this might be even more important. You need the agent to work every time.
Right, you can't have an agent that succeeds once and then fails the next 4 times. It destroys trust.
So how did they measure that?
Reliability was defined as the average success rate over 5 tries for any task that worked at least once.
Makes sense.
And across the models, reliability jumped from 74.5% to 79.0%. That 4.5% boost is huge for any mission-critical deployment.
And what's fascinating is why it gets more reliable. It's not just smarter, it's less random.
That is the core insight. The procedural memory suppresses what's called unwanted stochastic variance in the models.
In plain English.
LLMs are inherently a bit random. Their outputs have some chance involved, so an agent might succeed at a task once, but the next time, just due to that randomness, it tries something weird like scrolling to the top of the page for no reason.
So it's basically the agent getting distracted by its own creative randomness, a cognitive slip.
Precisely. By biasing the agent's decision toward a path that worked before, the path stored in preagis, it makes that successful behavior repeatable. It's like installing a good habit. It stops the model from going off on some random catastrophic tangent.
It keeps it focused. And the third dimension is efficiency. This is where you see the cost savings.
And this one saw a really dramatic improvement. The average number of steps to complete a task dropped from 25.2 steps down to 20.2.
A reduction of 5 steps per task on average, that has to be huge for both speed and cost.
The cost implications are immense. Every single step involves processing visuals, generating text for reasoning.
It's a call to the model.
It's a call to the model. So cutting 5 steps saves all those tokens and the API costs that go with them. Pragwas is guiding the agent on a more direct path. It cuts out the wandering around.
So the agent is taking the express lane it learned from experience instead of just wandering the side streets.
That's a good way to put it. And they check to see if this holds up as it learns more.
Right, does it get better with more memories?
It does. They ran a study on retrieval breadth, how many memories the agent checks. And performance generally went up as they searched more memories, and then it kind of leveled off at a plateau.
Which suggests the memories are genuinely helpful and generalize well.
The more successful runs it has to draw from, the more robust its decisions become.
Okay, so those are the key technical wins. But let's zoom out a bit. This isn't just about making web agents faster. The authors see this pointing to a different kind of human-AI partnership.
Right. A future where agents are working alongside us, augmenting what we can do, not just replacing us.
And for that partnership to actually work, the agent has to be personal.
Personalization is everything. Methods like Praxis are critical because users need to customize agents not just with their own data, but with their own unique procedures.
Yeah, if my company has a weird, specific way of filing expense reports in some ancient system.
You shouldn't have to wait for a global model to be retrained on it. You should be able to just show your agent how to do it, and it learns that habit instantly.
Which also has a privacy angle to it.
A huge one. You can teach your agent your private workflows, and that knowledge stays local. You're customizing its capabilities without having to share your company's secret sauce with a universal model developer.
So the agent goes from a generic tool to a truly personal assistant that knows your systems, your way of doing things.
And the most exciting future idea they mention is using this system to build what they call alignment agents.
Alignment agents. Tell me more about that, because that sounds like it goes beyond just getting the task done.
It does. So all the experiments we just talked about used objective success or failure as the learning signal.
Did it work or not? Simple.
Right. But you can modify Praxis to use user preference as the training signal instead.
So it stops caring only about success and starts optimizing for my personal style or convenience.
Precisely. Imagine the agent is just watching you work. Maybe you always ignore a certain pop-up, or you prefer a specific order of stacks that isn't the default. The agent can learn that.
It learns my habits, my little idiosyncrasies.
And it stores those preferences in its procedural memory. Over time, it would start to steer its own actions to match how you do things, eventually building a memory that encodes your specific preferences for how a task should be done.
Not just that it was done, but that it was done the way I like it.
So the agent becomes not just accurate, but actually aligned with your personal workflow.
That is incredibly powerful. The future of AI assistance isn't just getting the right answer, it's getting the right answer your way. So, to bring this whole deep dive together for you, what we have with Prec Eyes is a lightweight, state dependent memory that stores these little state to action habits. And it consistently improves an agent's accuracy, its reliability, and its efficiency. It's the agent learning essential local skills on the job.
And this idea of state-dependent memory really lets AI move beyond remembering facts to developing personalized, adaptable habits. Which leaves a big question for you, the listener. As agents learn not only what works, but also how you prefer for tasks to be done, will future AI assistants be defined more by the unique personalized routines they've learned from you, or by their massive universal pre-training? Think about that as you interact with your own digital tools this week.